2 blocks and an incline. 2 blocks and an incline. A frictionless inclined plane, okay, no friction there, height 0.65 meters, is set next to a rough horizontal section of the track. So down here we have friction. That's what rough means. Also, they tell you it has a coefficient of kinetic friction equal to 0.02. Block A of mass 1.5 kilograms is released from the top of the inclined plane. It slides down and collides in a perfect inelastic collision with block B. Block B has a mass of 2 kilograms. The 2-block system, they stick together, then move along the track until they stop. What is the initial potential energy of block A? Find the speed of block A at the bottom of the incline. Then right after the collision, what is the speed of the 2-block system? Okay, a few more parts of this. What is the energy of the 2-block system immediately after the collision? How much work is done by the friction force to stop the blocks? And how far will the 2-block system travel on the rough section of the track? What is the initial potential energy of block A? Well, that's just the GPE formula, mgh. We have the mass of block A, which is nicely shown up here. See how we list all the givens up here? Keep track of them. Times g times the height. So we put all our numbers in there and we get a GPE of 9.56 joules. Find the speed of block A at the bottom of the incline. You see how block A has moved down there and has a velocity indicated by the arrow? There's no friction on the incline, so there is no net external work done on block A as it slides down the incline. And now you might say, but wait a minute, isn't gravity doing work on it? Yes. However, we take that into account when we define gravitational potential energy. So we can ignore that, and since there's no friction, there's no other work on this thing. So we can use conservation of energy. So we have the energy at the top equals the energy at the bottom. So we have KE plus GPE top. There's a subscript T for top, and here's B for bottom. You're at rest at the top, so the KE is 0. And at the bottom, we're going to set GPE equal to 0 at the level plane there. So you will have no GPE. So all of the GPE at the top goes into the kinetic energy at the bottom. So here's our conservation of energy. Now we put in the equations, and it's all block A, so all the subscripts are block A. And the cool thing about this, once again, mass cancels out. The mass of the block doesn't matter to find its velocity. So we have GH, is equal to VA squared divided by 2. Just flip that equation around because we want to solve for VA. VA squared over 2 is GH. Divide both sides by 2, and then take the square root of both sides. So here is our key answer. That's where all the physics is. So the velocity only depends on the gravitational acceleration and the height, the vertical height of the object. You wouldn't have seen that if you just went ahead and plugged numbers in there and tried to solve for h. So that's why always do the algebra first. Put the numbers in and get 3.57 meters per second. This is very similar to the ballistic pendulum now, but first let's look at the nice picture here. We want to find the speed of the 2-block system, see how they're contacting each other and they're both moving off together. So this is a perfect inelastic collision. So we covered this part in the last section, so let's jump right to here. Okay, the individual momentums, however you want to say it, of each block is equal to their combined mass, because they're sticking together, times the velocity of the two together, which we're going to call AB. So the initial velocity of block B is 0, so that cancels out. And then we have MAVA equals MA plus MB times VAB right here. And we're solving for VAB, so we just switch the equation around and we get this. And what's going to be our next step to isolate VAB? Divide by MA plus MB, and that's what we have here. And once again, this is the important part of the problem. Go ahead and put your numbers in and make sure the units work, and they should if you do this right. Right, here's kilograms, they cancel, and we're left with meters per second. That's a good velocity unit. And we have 1.53 meters per second, which is less than the velocity that A had when it hit it. So that makes sense. What is the energy of the 2-block system immediately after the collision? Well, the blocks are at the lowest point of this problem, and we're defining that as GP is equal to 0. So all of their energy will be in KE. So the energy is in kinetic energy. So we have the combined mass, make sure you put both masses there, times the velocity that we found in the previous section, and make sure you square it. You do that and you get 4.10 joules. How much work is done by the friction force to stop the blocks? Remember early on we said that the horizontal piece here had friction. So this nice picture here shows the two blocks stuck together and they're not moving because there's no arrow. Initially, the two-block system has energy 4.10 joules. We found that from part D. The final energy has to be 0. EF is equal to 0 because the blocks are stopped. So we use the work energy equation. Initial energy plus work equals final energy. We take negative E0 on both sides, right, because we want to isolate work. So work is final energy minus initial energy. Final energy we just set as 0 because it's stopped. So our work will be negative the initial energy. So negative of 4.10 is, well, negative 4.10 joules. And it's nice that that turns out to be negative because friction force acts in the negative or opposite direction of the motion. And finally, how far will the two-block system, block A and B, travel on the rough section of the track before they come to a stop? That's kind of implicit. There's actually two ways to solve for the distance. One is using dynamics and energy, and the other way is dynamics and kinematics. We'll work both and see which one is quicker. We'll start on the dynamics and energy method. Let's use the equation for work. Work is F times X. Now why X? I think we've been using D, but the blocks are moving in the X direction, so we replace the D with X. The value of work has already been calculated. We need to create a free body diagram now to find the force. The blocks are moving in the X direction until they stop, and what stops them? The friction force, which acts in the negative X direction. There are no other X direction forces. So the normal force and the gravitational force, and the only trick here is it's for the combined mass, A plus B. They act in the Y direction. And we're drawing the acceleration vector to the left. Why? Because it's stopping, right? You had a velocity here, and the only way to stop it is to have a force and an acceleration to the left. The general form for friction is force of friction is mu k times the normal force. So we put in the normal force here for the friction, okay? So force of friction is minus mu k times the normal force. Now what is the normal force equal to? Well, from the free body diagram, you've got normal up and you've got mg down. So you put a positive for the normal force, a negative for the mg, and is it bouncing up and down? No. So the acceleration is 0. Therefore, the normal force is a combined mass of the blocks times g. Plug that into the normal force above, right? Here's our normal here, and that goes right there. And we get the force of friction is minus mu k, mass, combined mass, times g. That's our force of friction right there. We now use the definition of work. Work is the force, and in this case it's the force of friction times x. Well, we have force of friction from the previous slide. That's minus mu k mass times gx. And then we switch sides because we want to solve for x. And what do we have? We have, you know what, let me erase that. Hang on, because I want to highlight the next one. Here we go. We have this thing right here, and we want to solve that for x. We're going to do all that in one step. I'm going to take all of this and divide the left side by it and the right side. So x will be all by itself, and the right will be now a negative work over mu k ma plus b times g. We put in our numbers, and then you might be worried about this negative sign, right? Because you know the object's moving this way, so we'd like x to be positive. Fortunately, that negative sign cancels out with the negative work. We put the numbers in, and we get a distance of 5.98 meters before the block stops. Now let's work on the dynamics and kinematics approach. Kinematics is used to find the distance traveled. We have a final velocity, v is equal to 0, because the blocks come to a stop when they reach their farthest point. We have initial velocity, v sub ab. We need to find x, the distance the blocks travel before stopping. First, find the acceleration using dynamics. This will look repetitive because we already showed it, but I just want to have a complete solution here. Use your free body diagram. The blocks are going to move in this direction here until they come to a stop. And what will stop them? A force acting opposite their motion, which means the acceleration has to be to the left. The normal force and the gravitational force act in the y direction. How far will the two-block system travel on the rough section of track? Continued. So we know that we have a friction force acting to the left, so we give it a negative sign, that equals the mass of the combined blocks times the acceleration. Our general form for friction, by the way, if this seems deja vu-ish, we did it a little bit earlier, a few slides earlier, but we want to do it again just in case you're working here independently. So the force of friction is mu k times the normal force. So we substitute the mu k normal in force of friction, and we get this equation. Now we need to find the normal force. From the free body diagram, normal force is up, positive, mg is down, negative, and it equals 0 because the blocks are not bouncing up and down. So we have our normal force here, and we're going to substitute that into here. I think the last time I did this I said substitute it into there, but that's kind of the same thing. So here was our force without the value for the normal. We put the normal force in here like this, and then look what happens out. The masses cancel out. So we have minus mu kg equals a. We reverse it and find the acceleration is just minus the coefficient of friction times g. There's no mass there, so once again the mass doesn't matter. Plug in our numbers and we get a negative acceleration, which is great because the free body diagram, we expected it that way, and that's how it showed up mathematically, and it's a friction force. We now have initial velocity, final velocity, and a. Which of the three kinematics equations should we use to find the displacement x? Third kinematics equation. Okay, and why is that? There's no time here, all right? So we don't use 1 or 2. So here's our third kinematics. Final velocity is 0, and this is the one exception to do only in the algebra first before you put a number in. If we can substitute a 0 in, that gets rid of something. That makes it a lot easier. So once we have this, we can put a negative 2ax on the left side. Why? Because we're solving for x. Divide through by 2a. Do it all at once. Okay, nothing that says we have to divide it by 2 first and then a. They're stuck together. Combine them and also pick up the negative sign too. Divide by negative 2a. So here's our final distance. Nice and neat. Plug in our numbers, and once again, don't worry about this negative sign. Why? Because the acceleration's negative. Negative times a negative is a positive, and we will find that the distance is 5.97 meters. So we had our two approaches. Dynamics and energy found a stopping distance of 5.98. Dynamics and kinematics found 5.97. Now that doesn't mean they came up with different answers. That's basically the same answer because we did different calculations with different roundings. But which were quicker? Most of the time, or you can just say many times, dynamics and energy works quicker than dynamics and kinematics.